Welcome to this explainer. For so many students staring down the barrel of advanced math, the formulas can honestly just feel like this massive, intimidating mountain of abstract symbols. Well, today, we're completely flipping the script on that. We're going to strip away all that intimidation and look directly at the highly visual geometric foundation of calculus. It is a pretty huge leap, right? How exactly do we get from drawing a simple little dot on a piece of grid paper to calculating the crazy curves, infinite slopes, and vast volumes you find in calculus? It literally seems like magic. But the truth is, every single complex idea in math starts with something incredibly simple. So here is our roadmap for this bottom-up journey. We'll start with points, group them into graphs, define them with equations, measure them with distance, shape them with geometry, and finally arrive right at the doorstep of calculus. We've got to start by reframing how we actually see these things. We all know what a point is. Say the coordinates 2, 3. That just means go 2 steps right, 3 steps up. Super simple. But a graph? It isn't just some random line drawn on a page. It is a massive, bustling collection of specific coordinates. It is literally a crowd of points that are all just following the exact same rule. Now, what's genuinely fascinating here is how adding just a few more specific points completely transforms the pattern you're looking at. Take a look at this. On the left, if we plot 1, 1, 2, 2, and 3, 3, they line up perfectly to form a straight diagonal line. But on the right, if we change the rule, say we make it so our points follow a rule where a number is multiplied by itself, boom. That straight line instantly bends into a really smooth, elegant curve. And honestly, this hits the nail right on the head when it comes to the biggest secret of analytic geometry. Algebra and geometry are really just two different languages saying the exact same thing. The equation is the mathematical rule we write down, like y equals x squared. But the graph? That is simply the visual picture of that rule in action. Think of the equation as the script and the graph as the movie. Let's look at a few of those simple scripts. The equation y equals x creates a perfect diagonal line shooting up to the right. Its twin, y equals negative x, creates the exact mirror image, a line going down. But what if we throw an absolute value into the mix? Well, absolute values turn any negative number positive, right? So the graph of y equals the absolute value of x actually combines both of those lines. When x is positive, it goes up. When x is negative, the absolute value flips it, so it still goes up. The result is this perfect, sharp, V-shaped graph. So that brings us to a really crucial question. If an equation can draw us a beautiful picture, can the picture give us an equation? Can we actually run this whole thing in reverse? What if, say, I want a single, unified mathematical rule that draws both of those diagonal lines, y equals x and y equals negative x, at the exact same time, but without using absolute values? Is that even possible? Actually, yes, we can absolutely do that. If we just rewrite our two-line equations as y minus x equals 0 and y plus x equals 0, we can multiply them together. It is like a neat little algebraic magic trick using the difference of squares, and it leaves us with y squared minus x squared equals 0. Thanks to the zero product rule, this single, elegant formula represents the complete union of both diagonal lines. It is just a gorgeous marriage of algebra and geometry. Okay, let's take a massive conceptual leap now and see what happens when we tweak just one tiny symbol. What happens when we swap out an equal sign for an inequality? Well, an equation gives us a strict, rigid line. It is like walking a tightrope. But an inequality, that opens things up entirely and gives us a massive, shaded region. To see why this happens, just look at the inequality y is greater than or equal to x. Because y can be equal to x or bigger than it, our solution is no longer trapped on that tightrope. If you test a point out in the wild, like 2, 5, well, 5 is for sure greater than 2. That means every single point in that entire endless space above the diagonal boundary is part of our solution. Our answer isn't a line anymore. It is a whole area. Now check out this really fascinating one. X is less than 2. Notice anything missing there? Yeah, there is no y in that inequality at all. But even if an inequality completely ignores the y-axis, it still creates a region. It simply drops this vertical dashed wall right at x equals 2. And since the rule is strictly less than, the boundary line is dashed, because the wall itself isn't technically included. But every single point to the left of that wall, whether y is a positive 100 or a negative million, is a totally valid solution. All right, moving on to the distance formula. From coordinates to geometry, let's add a new tool to our visual toolbox and figure out exactly how far apart all these points actually are. Listen, if I give you two random points on a graph and ask for the straight line distance between them, please do not try to memorize some complex formula. Instead, just drop a vertical line straight down from one point and shoot a horizontal line across from the other. By doing that, you instantly build a simple, perfect right triangle right around your 2 points. And finding the lengths of that triangle's sides, it is incredibly intuitive. To find how long the horizontal bottom edge is, you just subtract your 2 x-coordinates. To find how tall the vertical edge is, subtract your 2 y-coordinates. That is literally it. You have just found the base and the height of your triangle. But wait, if you look back at that famous distance formula you were probably forced to memorize in school, you'll notice a catch. There is a very specific reason we have to square those subtracted numbers before we add them up. I mean, why not just subtract them and call it a day? The answer is pretty simple. Distance has to work no matter which direction you measure it. If you subtract 5 from 2, you get -3. But a distance cannot be negative, right? You can't walk -3 miles. So squaring the differences acts as this brilliant mathematical filter. When you square -3, it becomes a +9. It elegantly erases any of those negative directions, so our distance is always positive before we finally take the square root. And honestly, this reveals the biggest secret of them all. That big, intimidating distance formula with its giant square root symbol and confusing subscript is literally just the Pythagorean theorem wearing a geometric disguise. You are just doing a squared plus b squared equals c squared right there on the coordinate grid. It is not advanced magic, it is just basic triangles. It gets better. When we plug real points into this formula, these beautiful classic patterns start to emerge. Say we want the distance between the point 1, 2 and 4, 6. The horizontal difference is 3. The vertical difference is 4. Well, 3 squared plus 4 squared is 9 plus 16, which equals 25. Take the square root and you get 5. We just visually built a perfect 3, 4, 5 right triangle. The exact same thing happens with points 0, 0 and 6, 8, popping out a perfect 6, 8, 10 triangle. We can even take this a step further and use the converse of the Pythagorean theorem to mathematically prove the exact shape of any triangle drawn on our plane. Think about it. If we calculate the distances between 3 random points and find the sides are the square root of 73, another square root of 73, and the square root of 146, well, 73 plus 73 is exactly 146. Because the 2 shorter sides squared equal the longest side squared, we have just mathematically proven it is a right triangle. And since 2 sides are identical, it is an isosceles right triangle. Once you know that, calculating its exact area is a total breeze. So, before we reveal our final destination, let's quickly review the 6 fundamental geometric building blocks. We started with points, which are coordinates. We grouped them into graphs based on rules. We learned that equations draw curves, while inequalities shade entire regions. We used the distance formula to measure space and realized it is literally just the Pythagorean theorem in action. Looking at this snowball progression, you can see exactly how mapping simple points directly paves the road to advanced mathematics. None of these concepts exist in a vacuum. The coordinate plane leads to equations. Equations let us measure distance. Distance unlocks geometry. And geometry, well, geometry is the final stepping stone. Because this geometric foundation is the exact machinery behind calculus. When a student eventually encounters a derivative, they shouldn't panic. They're simply studying the slope of a curve, which is just points and equations. When they hit an integral, they're just calculating the area of a shaded region, which is just inequalities in geometry. You absolutely cannot navigate the deeper, complex parts of calculus without first mastering this coordinate plane. So I am going to leave you with this final thought. You've seen how a single, simple dot evolves into complex regions and mathematically proven shapes. But armed with these foundational visual rules, what happens when we push them to their absolute limits? Are you ready to conquer the infinite curves and shifting slopes of true calculus? Think about it, and we will see you next time.